Welcome. This recording is to help you complete the Unit 2 portfolio in PreCalculus B. Particularly, we're going to be using curve fitting with sine and cosine functions. So we're going to be modifying amplitude, period, phase shift, and other things, vertical shift. So I'm going to be using Desmos. There is a worksheet for you to download and fill out, but I'd like you to include screenshots from Desmos. If you use another application, that's fine. This can be done in Microsoft Excel and other programs as well, but I'm going to use Desmos. It works really well for curve fitting. All right, so you are asked to research a city, a major city, or not necessarily even a major city, but a city. It says near you, but it wants multiple latitudes. Latitude affects temperature, and so we're going to be recording average monthly high temperatures for these things. So let's take a web browser here. And I'm just going to type average monthly temperature. And I'm going to do Edmonton, Canada. Okay, because I want a city that's way far north, and I'm going to record data for 3 different cities at 3 different latitudes. So I want a variety. And we'll see what latitude does to average temperatures. Okay, and so here we go. Here's weather history for Edmonton, Alberta, Canada, which doesn't give me the latitude. It doesn't, but I can look up the latitude. Okay, and so we can click on each of these and record the values for the average daily high temperatures. And what you see are the low and high. So I'm going to record the high. Looks like January 22 was the high and 4 was the average low. And so let's go ahead and make a table. So click the plus in Desmos, table. And month number 1, the average monthly high was 22 degrees. Okay, 27 for February. Okay, let's collect a number of them here. 36, 51. 64, 70. 75, 73. One nice thing about Alberta, Canada, it doesn't typically get very hot. 64, 51. And 34 and 24. Okay. All right. And one really cool thing here, if you look in Desmos and down here on the bottom left, there's a little magnifying glass with a plus sign. It's zoom to fit. So you can automatically zoom your graph to fit. All right. So we have a nice little peak in the middle of the year. Note that the summer months are hotter. That's because Alberta, Canada or Edmonton, Canada is in the northern hemisphere. We would see the reverse if we had a southern hemisphere city. So like if I chose Sydney, Australia, this whole thing would be inverted. It would be an upside down U or a U right side up. All right, so now we want to fit our trig function here to it. Now, there is a curve fitting routine or a curve fitting algorithm in Desmos, and I want to show you that, but I want to fool with this manually first. Okay, so we notice the peak, the kind of sinusoidal peak here. So I'm going to just say y equals sine x, and we're going to start modifying. Okay, the first thing I note is that sine x is centered at 0. But I want to center this in the middle of this. So I'm going to note the lowest temperature, 22, and the highest temperature, 75. And I want to go halfway between 22 and 75. So I'm just going to do this. 22 plus 75 divided by 2 is 48.5. Okay, so the middle of that is 48.5, the midpoint. So I'm going to say plus 48.5. So now we've risen, we've brought up the sine function so that it has the correct height. Now we want to have the correct amplitude, right? And so amplitude is modified by putting a multiplier in front of sine. Okay, now we want the amplitude to go all the way down to 22, and it's at 48.5. So what is 48.5 minus 22? 26.5. So I'm going to put 26.5 right here, and now we've got the correct amplitude. Now I may still fiddle with these values, but that's kind of the idea. Okay. Now the period. The period I want the sine function to have a period of 12 months, right? So it's going to repeat every 12 months. But the natural repeating period for sine is 2 pi, right? So pi over 2 to 5 pi over 2. 5 pi over 2 minus pi over 2 is 4 pi over 2, or 2 pi. Okay, so we need to change that period from 2 pi to 12. Okay, this takes a little bit of finagling here. Let me bring up a scratch paper here. Right now the period is 2 pi. I need the period to be 12. Okay, so how do I change 2 pi into 12? Well, let's see. I would multiply it 2 pi times 12 divided by 2 pi, right? Or to reduce 2 pi times 6 divided by pi. Okay? So if I multiply by 6 divided by pi, which would compress it, we need to remember that x is inverse, so it's opposite. So we need to divide by 6 divided by pi. Okay, so here we go. Let's go to Desmos. Oh, there it is. Okay. All right, so we're going to replace x with, okay, 6 divided by pi divided by 6 divided by pi is, so we're going to invert and multiply. So we're going to say pi divided by 6. There we go. Okay, and now, now because I multiplied by pi divided by 6, my sine function has the correct period. It's repeating once every 12 years. So we've got just one more change to make, and that is to phase shift. That is to shift this thing. Probably the shortest way would be to the right. I could shift to the left as well. But I want to note the peak occurs at 3 on my sine function. I need the peak to occur at 7. So I need to shift to the right 4 units. Okay. So I'm going to put another parentheses around my x. This is important, this parentheses. And I'm going to say minus 4. And there we go. Okay. All right, and then we got a pretty good fit. Now, I will note that the peak seems to occur actually a little bit late, and that is a trend I see because I've done this assignment quite a few times. A trend I've seen is that the actual heat arrives a little bit late. So, for example, the shortest day of the year is called the winter solstice. That occurs typically December 20, I want to say 21, but it might be 23. Okay, some people think it's Christmas. It's not, and it never has been. But the shortest day of the year actually precedes the coldest, typically coldest day of the month. The coldest day of the month is typically in January. And so it takes a while, and the same with the hottest day of the month. The hottest day of the month, the longest day of the month, the summer solstice actually occurs in June. But July is typically hotter than June. And so there's a little bit of a delay, and because it takes a while for the heat of the surface of the Earth to absorb or to dissipate heat. So there's a little bit of science to that. Okay. All right. Now, I do want to show you a way that Desmos automatically does all this, but I wanted you to play with this too first here. So, and that's this. So y, okay, and y1, actually, yeah, y1 tilde, and now I'm going to insert coefficients instead of numbers. A sine b x minus c plus d. Okay, and can't say x1. There we go. All right, and it fits it for me. And notice what it says here. It says I said my amplitude modifier was 26.5. Their amplifier, Desmos's, was 27.42. Okay, so a little bit bigger. Okay, and that's to be expected, actually. I anticipated the actual high would be the highest temperature recorded for a month, but when we increase resolution, it can actually go a bit higher and lower. Okay, and my B modifier, my amplitude or period modifier is 0.5, so that basically is about 2, right? So 2 times. Okay, and my C is my phase shift to the right, so they shifted to the right by 3.9 instead of 4, and vertical shift was 48.3 instead of 48.5. Okay, and this is using an algorithm called least squares to minimize the difference between the data points and the actual. So you're going to get a slightly better fit this way. Okay, do remember it is a tilde. Do remember you need to add the subscript, so y1 and x1 when you do this. And Desmos will do this with literally any function. Okay, all right, so I'm going to leave that here. And we're going to go ahead and do this again for another city, okay? And I'm going to I'm going to get rid of this just to simplify here. All right, so let's research another city. Now I want another city that's further south than Edmonton, Canada. That could go Seattle. That's probably not far enough south. Let's go San Francisco. That's a well-known city, and it's still in the northern hemisphere. And okay, average monthly temperature, San Francisco. Okay, and here we go. All right, so we're going to record. We're going to make a new table. Okay, and this one's going to be x2 and y2. All right, we got 59 and 62. Okay, 66 and 68. '73 and 78. Now, one thing that modifies the temperature in San Francisco is it's right on the ocean, and so it doesn't tend to get very hot. 81, 81. Okay, and 80 and 75. If I'd chosen Phoenix, Arizona, you'd see very different results. because that's inland, 65 and 59. Okay, put the month numbers in. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so you'll notice the difference here in the peaks, right? So let's do the math again. Okay, we're going to create a graph to go through this. So first I'm going to just start with y equals sine x. Okay, and I'm going to modify it here. So our low is 59, our high is 81. The average of 59 and 81 is 70. So I'm going to add 70 to my sine function to get it up where it belongs. Amplitude, okay, we brought it up to 70, but the low is 59. So the amplitude modifier, 70 minus 59 is 11. So I'm going to put 11 in front of sine x to get the amplitude right. Okay, the period multiplier is going to be pretty much the same, so it's pi divided by 6. That's to change from a period of 2 pi, which is about 6.3. Yeah, 6.3. Okay, to 12. So we're going to do pi divided by 6. There we go. Get the amplitude, and let's modify. Now the peak seems to occur, you got 2 months where the peak is the same. So the peak is going to occur in between. So 7.5. 7.5 minus 3 is 4.5. So, okay, minus 4.5. And there we go. Okay. Now notice the high temperature is only slightly higher than Edmonton, Canada, but the low, it doesn't get nearly as low. And this is a pattern that we're going to discuss later on here. All right. So, and just to review one more time, if we wanted to do this automatically, it would be y2 tilde, because it distinguishes between y2 and y1. Okay, a sine pi divided by, not the pi divided by 6. I want to go here. Now, we could force it to be pi over 6 by putting pi over 6, but I'm going to do b x2 minus c plus d. Okay, and there we go. And that's a pretty close fit to what we came up with before. Okay, all right. So that's how you do automatic. But I really think for the purpose of this assignment, you really want to modify it yourself, just to get used to what each number does, because that's the object of this lesson. Okay, one more. We need to go with another city. So let's go with another city that is further south than San Francisco. How about Mexico City? That's still northern hemisphere, so we'll still see the same pattern here. Okay, Mexico City. Okay, now by the way, when it comes to yours, please don't use my cities, use your own. Okay, so here we go. I'm going to add a table with x3 and y3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And let's go grab our number 65, 69. Okay, 74, 76. 76, 73. 70, 70. 69, 68. And 66 and 64. Note that it never really gets cold. What was that again? 66 and 64, yeah. 66, 64. Okay, so there's the purple dots. I note that the spike occurs in January, February, March, April, and May. So in spring, that's where the high temperature occurred. It leaves me wondering what happened in the summer in Mexico City that caused the temperatures to be so low. But have to do a little research to find out. There might have been a hurricane or something. They do get weather patterns off the Gulf. And that actually probably is it. The weather patterns off the Gulf can create a little chaos. Plus, the flatter your temperature variance, the more chaotic it's going to tend to be. The more chaotic the pattern, because the weather is not dominated by the position of the sun overhead. The closer you are to the equator, the more consistent the sun is. To give you an example, I spent a year in the Marshall Islands, which is at 7 degrees north latitude. So that's within the 10-degree boundary of what we call the tropics. Not the subtropics, but the tropics. It was 86 degrees average temperature every month. It never went high, it never went higher, it never went much significantly lower. And so basically this curve flattens out when you're at the equator. And as I mentioned, if you're in the southern hemisphere, it reverses. The peak is down, it is on the sides. All right, so let's fit our curve here. Okay, so y equals sine x. I'm going to sneeze. Ah, bless me. All right. Okay, and let's figure out our low seems to be 64. Our high is 76. 64 plus 76 divided by 2 is 70. So same average temperature as in San Francisco. Okay. And our amplitude is 70 minus 64. 70 minus 64 is 6. So 6. Okay. And same period multiplier. We want to change from a period of 2 pi to 12. So I'm going to multiply by pi divided by 6. Okay. And phase shift. Our peak seems to occur here. Now this phase shift is going to be really difficult here. Well, our peak seems to occur here. 76, yeah, so 5, so only 1.5 to the right. So we've got a little bit of a decision to make here. So if I went plus 1.5 or minus 1.5, okay, it matches the peak but not the rest of the function. So I'm going to fiddle with this. If I go 4, and I'm going to go 3. I think 3 kind of splits the difference. 2.5. Yeah, 2.5 is probably the best. Okay. All right. So really interesting phenomenon. Notice that the highest temperature doesn't seem to change much between these cities. They both have, all three have about the same high temperature. But where we see the difference is in the flatness of the sine curve, and that's because the further you get toward the equator, the less variance you're going to have, and toward completely flat at the equator. Be interesting if we did like Nome, Alaska, and did a really far north city to see how much variance there is. You know, because then you're in the Arctic, and you actually have. There's a region on the planet, or 2 regions on the planet, where part of the year the sun never comes up above the horizon. It never shines. And then there's another part of the year where the sun is up all the time. It never goes down. So it's really kind of fascinating. All right. So hopefully that makes sense. Well, just out of curiosity, let's do the fit. So y3 tilde a sine a or b x minus x3 minus C plus D. Okay? And it shifts there. This is the purple here. It shifts a little bit further left than I did and decreases the magnitude, the amplitude. Interesting. Okay. All right. So please include with your worksheet a screenshot of your combined graph. I'd like to see the results of your graph. All right. Feel free to book a live lesson if you need any help.